There we go. All right, so we have mg, like we've made this substitution for the tension force. We're multiplying it by sine, and this equals mr omega squared. Does anyone see anything that we can cancel out? Anything that we can cancel out?
The m.
Yep, the m, very good. So I can cancel this out. And then what I'm going to do is I'm going to just rearrange this. So I still have, I'm just going to have rearrange this slightly. So this is going to be g times sine theta divided by cosine of theta. So all I did is I changed the form of this just a little. I'm just multiplying that. And this equals r omega squared. Does anyone see a substitution that I can make? It's more like a math thing that you would do from like some
Tangent.
topic. Yeah, so I can make a substitution. This term right here is just the tangent of theta. So this is now just going to equal g times the tangent of theta, and that's going to equal r omega squared. So what I'd like to do is I'd like to leave the problem to you at this point, and can you finish it and then determine, is the answer going to be A, B, or C? So I'm going to give you 60 seconds to do that.
Which variable do we solve for again?
You're solving, so like, is it okay if I switch screens, guys? Is it okay if I switch?
Yes.
Okay, I'll put this one back up. Okay, can you see the problem again?
No.
You can't see the problem? Okay, hang on one second. Okay, can you see it now? Okay.
Yeah.
At about 30 more seconds. About 20 more seconds. All right, about 9. All right, what do you guys say? Can you chat me what your answer is? Can you just like do a chat what your answer is? Yeah, very good, guys. Very good. Very, very good. Yeah, everyone got it right. Good work. Good work. Now, there's one little quick technique. So this took a long time to do this one problem, but it was intended to be for review and to really kind of get to really kind of stress building that memory to just do these problems really quickly. What I'd like to do is show you, let's say, this is a technique that you can do on a lot of problems. So what I'm going to do is I'm just going to write down like for choice A. Okay, so what I want to do is to show you a technique that you can reduce the number of possible answers, and you can do it really quickly. So A, the answer looked like omega squared over r times g. And letter B was very similar to this one. It was g omega squared over r. And C was omega r squared over g. And what was the last one there? D looked very similar to D looked very similar to letter C. Now, one of the things that you can usually do right away, so what you were looking for was the tangent, okay? And I said this earlier, whenever you do a tangent of something, your answer is like the answer that you're going to get is a unitless number. Okay, so what you want to do, if you want to do like just like a quick problem solving technique, is see if the units actually give you or see if these things, the base units, actually give you a unitless number. So like as an example, the base units for angular velocity were like 1/seconds. They were radians over seconds, but radian isn't a real unit. It has no like physical dimensions. So the unit for the radian or angular velocity was 1/seconds. The unit for r, for the distance, the radius, is going to be units of meters. So I'm going to write that as m square the whole thing. And then divide that by the units for the gravitational acceleration, which are going to be meters per second squared. And if we kind of just do some algebra, we see on the top, we have meters squared over second squared divided by meters over second squared, excuse me. So I think if we just cancel out the like terms, we're going to see that this works out to be units of meters per meter per second, I think. Yeah, meters per second. Okay. And since we have since this one's units are not like anything, since this actually has units, like letter C and therefore letter D can't be our possible answers. Okay, so we've eliminated two answers, and the reason that we can eliminate both is these are just reciprocals of each other. So if there's base units in our final answer, there'll be base units for both C and D. But in this case, like, so we now know the answer is going to be either A or B, okay? And so that's going to be the tricky part, like in terms of, excuse me, like as we solve these problems, like just to check this, right? We can say that omega is 1/seconds squared, this because omega angular velocity is 1/seconds for their base units, times r in this case is just an m, and then in this case we're over meters per second squared. Okay, and if we do this out, we see that on the top we get meters per second squared, and then this meters per second squared. And then when we do these units out, like the unit analysis, those two just cancel out. So this is just 1. So the number that we get is a unitless number. And so like in this case, this is going to be like choice A or choice B if you're in a bind and you're just trying to get some problems done, trying to increase your chances of getting a problem that you're not certain of right. This will eliminate, this method eliminates half of the problem. So you are then stuck with choosing between two values. Okay. Questions on this? Any questions? No? Okay. All right, so
Ted,
yeah.
so I was wondering if later, if we have some time, can we go over the homework, because some of the questions were very hard.
Yeah, like let's actually do that. Let's go over the homework before we kind of go on. So can someone just help me keep track of time? Give me a moment also to get the homework open. Is it this one?
Yeah.
So yeah, which one did you want to go over?
On number 8.
Okay, give me one moment. I'm going to kind of transfer it over to my other screen, and then we can kind of, it'll be easier to do it that way. Okay, so number 8, you said?
Yeah.
All right, so so this one says the Earth mass, it gives us the mass, rotates around the sun in an orbit that is approximately circular, with a radius of 1.5 times 10 to the 11th meters. Okay, estimate the orbital speed of the Earth around the sun. Okay. Okay, so I'm just going to summarize some of that information that they gave us so that we can see it. So m equals 6 times 10 to the 24th kilograms. The radius, the Earth-Sun radius is 1.5 times 10 to the 11th meters. And what we're looking at is, so we have the sun and we have the Earth revolving around it. Okay, and what we're looking at is estimate the orbital speed of the Earth around the sun. So when they say orbital, what kind of speed are they looking for when they say orbital? Are they looking for angular velocity, or are they looking for tangential velocity?
Would it be tangential since like Earth is like that specific spot on the whole like orbit?
Yeah, and so like I'm just kind of like double checking the question. So the orbital speed, in this case, I'm thinking that they mean the tangential velocity. Like sometimes their wording kind of can be like misleading. So let's go ahead and find it the tangential velocity. So let me just diagram one thing. We know this distance here. Okay. So we know this distance. Now, so a couple of the things that we know, so we can actually, so we know that this is moving at constant velocity in a straight line. So one thing that we need to know to figure out the orbital speed, right, or like the tangential velocity, is some of the information, like the number information that they don't give us in this problem. So like as an example, I know that Earth revolves around the sun once a year, okay? So like there's one revolution. Let me write this a little bit better than that. I'm going to write it like this. I know that the Earth revolves, there's one revolution around the sun per one Earth year. Okay. And now like I'm going to guess, because like we want to be in our SI units, we want to be in units of seconds. So what I'm going to do is I'm going to try to find the number of seconds in a year. And I basically do that just by like multiplying things out. I know that like 1 year has 365 days, right? And that allows me to cancel out the year with this year, and now I'm in units of days. I know that, so I know that there's 365 days, and I know that 1 day has 24 hours. Okay, and this allows me to kind of cancel out days with days. Okay, and now I'm in units of hours. And if you know that there's 3,600 seconds in an hour, that's great, but you can also kind of like figure that out as well. So I'll just do it like in case you need to see like where that 3,600 number comes from. So I know that like 1 hour has 60 minutes, and that allows me to cancel hours with hours. And then I know that 1 minute has 60 seconds, and this allows me to kind of cancel this out. So when I multiply all of these numbers out, I have the number of time, right now I actually have the angular velocity, and I'll show that in a moment. So like what I've just solved right here, this is delta theta over delta t. This is our omega. This is our angular velocity. So like, it's in this case, it's 1 revolution. Can someone tell me what 365 times 24 times 3,600 is?
3.15 times 10 to the power of 7
3.15 times 10 to the power 7.
seconds. Yeah.
Yep, very good. So like this would be like the angular, this is like the angular velocity, okay? The change in angle per change in time. So in 1 year, so there's one revolution every 3.15 times 10 to the 7 seconds, which what does that number mean? It's just like the unit per year. But if we want to find the tangential velocity now, okay, so we can just do, let's do that in a different color. So we can just do V equals R times omega, okay? Now in this problem, they tell us what the R is. They told us it was 1.5 times 10 to the 11th. So now I can just plug that information in. So times 10 to the 11th, but it was 1.5, okay. So 1.5 times 10 to the 11th meters. And my angular velocity, I found that just by kind of like taking some information that I know. So this is like 1 revolution per 3.15 times 10 to the 7th seconds. And just like a meter times a radian is a meter times like a revolution is still just a meter. Okay, this is like not a real like unit in the sense it has physical dimensions. So can someone tell me what 1.5 times 10 to the 11th divided by 3.15 times 10 to the 6th or 10 to the 7th is?
4,761.9.
4,000. So I'll call that 4,700, just like this.
Yeah, and 61. Yeah, point.
Oh, like we'll ignore the 61 just because like this number only has 2 sig figs. So we'll try to, and that would be the units on this would be meters per second.
Tim, I have a question.
Yeah.
So does that mean that like omega, it's delta theta over time? So theta is also revolution, it's the same thing?
Yeah, so like 1 revolution equals a change in 360 degrees, which equals 2 pi radians. So like in this case, we wanted to think about revolutions. We didn't want to think about like degrees or anything like that. Does that one make sense?
Yeah, thank you.
Okay.
So whenever,
go ahead. Yeah.
So whenever we have to find tangential velocity, we can go through this, right?
Absolutely. Yeah.
Okay.
No, definitely. Like do this method. Like for this unit, for finding angular velocity, what I find the easiest, like in terms of like, I find the formulas in topic 6.1 a little bit confusing because there's like one with like just so much information, it becomes like 4 pi r squared, something like that. And I just find it easier to kind of go through the first principle method for some of these problems. Now the other part, so that was like part A.
Wait, Tim?
Yeah. Go ahead.
In the book, it says it has a different answer.
Can you tell me, or can you tell me what the number they say is?
Yeah, 30 kilometers per second.
Oh, so yeah, okay, so check it out. So they give it to you in kilometers per second, so then say 30?
Yeah.
Let me just check that.
I think it's a unit.
Give me one moment. Let me just open up my. And just give me one moment. I'm going to check the. Actually, I just checked. I have this book right here. Andy, what page is that on? Do you know, on the back of the book?
It's on page 536.
30 kilometers per second. Can I just double check the number that you got on the bottom? Well, actually, I see it, so I'm just going to check a few things in my calculator. Okay. Oh, do you know what I'm thinking we should have done? I think we actually did need to, we had to actually convert this number right here, revolutions. We needed to actually convert that to radians, right? So in this case, let's fix this one problem here. So we have, or this mistake right here, excuse me. So we have revolutions, right? So this should actually be, 1 revolution equals 2 pi radians. So I think that should probably fix our answer. Actually, that does fix our answer. So I think when we do this, so like now this just equals 2 pi over this big number here. Just write that out. And so when we go down to this formula right here, we actually do need to put the 2 pi into this formula. So this one should actually be 2 pi. So can you now double check that number? I think if we take this number maybe, and I think if we did this part, if we multiply that, if we just multiply that by 2 pi, could you tell me what you get?
Uh, 29,500.
29,500. And that's, in this case, this is meters per second. But if we convert this over to kilometers per second, which is what the book gives us the answer in. So I'm going to just say like 1 meter is, excuse me, 1,000 meters. 1,000 meters is 1 km. So if we cancel this with that, so I think we get, in this case, 29.5 kilometers per second, which is what the book got.
Yeah, they just rounded to a 30.
Yeah, they're just for sig figs, yeah. Did we still need to do I'll keep going and do letter B, would that help? Or did you want to try B by yourself now?
And yeah, if we have the speed, then B is easy.
Okay.
The next question that was challenging was also 9, but I don't know if you have time for that, but 9. I mean 10, yeah, 10. There was no 9, it was the next one.
Yeah, like we go till 2:45 today, I think. Is that right? Okay, yeah, maybe it's better to make sure that, we're good on these problems. So this one, number 10 says, so what I'll do is, okay, we're gonna draw a free body diagram. So I guess let's do that. Yeah, okay, yeah, let's do all of 10 together. So this one says, a cylinder of radius 5 rotates about its vertical axis. A girl stands inside the cylinder. Oh yeah, this is kind of like the do now that we did today. A little bit more complicated though. The floor is suddenly lowered by the girl stands glued to the wall. Has anyone seen this before? Has anyone gone to like an amusement park and seen this this ride before? Yeah, no, okay, so hold on. To help us visualize this, hang on 1 second. To help us visualize this, let me show you what this actually looks like. So there's, can you guys see my screen? Okay? All right, so what this ride is based, I'm gonna just turn the volume down. So they're in this room, okay? And you, can you guys just give me a thumbs up? You see the ride part right back here? Okay. So what this is this is like an amusement park ride, and you have this like little cylindrical room, and you get in, and the ride starts to speed up. And after a few minutes, what happened of speeding up, or like a minute, the floor drops out from underneath the people. So what I'm going to do is I'm going to play this just so you see what's going on with
the dance or do anything else while the ride is in motion. Okay, guys?
So hopefully I shut the volume off and you can't hear it. Okay. So if you look, they start spinning slowly. Hopefully you guys don't get sick staring at the screen. But you know, this starts to spin slowly, and then it starts to move faster and faster and faster. And I think that's what you can see with if you're staring at it and getting motion sickness. But then what happens is the floor like is lowered out from underneath them. And if you can see it, I'm going to pause it for a moment, but one, see how blurry they are. But also if you notice that, you know, it's not the best video in the world, but the floor is no longer beneath their feet. The floor dropped out from beneath their feet, and they're just held there against the wall. And the force that's actually holding them is friction. Let's just see if you can see it a little bit better. Speed it up a little. But then if you check it out, like the floor comes back up, and then what happens is, you know, like they can get off the ride. Okay, so let's take a look at this problem again. Okay, so so just going back to this one, this problem, it's a kind of a lag. There we go. So the cylinder has a radius of 5 meters, and it rotates, and it tells us some more information. The floor suddenly lowered by the girl stays glued to the wall. The coefficient of friction between the girl and the wall. So the first thing so let's just kind of draw what this sort of looks like. So it's kind of like we have this cylinder, the girl's inside the cylinder, you know, the room starts to rotate. So here she is right here. Okay. So we know that the radius, so let's do that different color. So we know the radius of this room is, in this case, R is 5 meters. And just check a couple of things. And the other piece of information they tell us is the coefficient of is that static friction? No, in this case, I'm going to guess it's, oh, no, sorry, it should be static. So they tell us it's 0.6. And the first thing they want us to do is draw a free body diagram. Okay, so let's go ahead and draw the free body diagram for the forces acting on this person. So I'm going to give you guys like 1 minute. So here's the person. See if you guys can draw and identify all of the forces acting on this person. And let's just kind of say like, this is like towards the center of the circle. Just in terms of like a reference point. All right, can you guys show me like with like, you know, fingers, how many forces are acting on the person inside of the cylinder?
Would there be normal force from the cylinder?
Yeah, very good. Yeah, so in this case, there's going to be a few forces, and one of those forces, the force between the wall and the person, right? So just to kind of give you like, this is the vertical direction right here. Okay, so what's basically happening is the wall is the force, the centripetal force in this case, causing the person to keep moving in a circular motion. So let's call this R, okay. What are the other forces acting on the person? What's the one force whenever you have a person or a thing with mass that we
Weight.
all, yeah, so
Weight.
there's gonna be weight force, very good.
Weight.
So weight is in the downward direction, we'll call it with a little W. What other force is still acting on this person?
Friction.
Yeah, what direction is friction acting?
Opposite R, right? Or-
Not opposite R.
but doesn't it keep the person on the wall?
No, so yeah, like, so in this case, the frictional force is gonna act in the upward direction. Because what's gonna happen is gravity, so like, let me just back that up a little. So if you imagine this, right? So the normal force, the R here comes from the wall. So the wall is literally pushing the person towards the center of the cylinder, okay? And then, so like, there's no other forces acting in the X direction. It's just the wall, and that wall is your centripetal force. But then we have forces in the vertical direction. Now, in this case, we have weight that's in the downward direction because gravity always pulls objects towards the center of the earth. But what we now need is we need to have a force to balance the weight force so that this person doesn't just slide down the wall. So in this case, the force that's going to be opposite in direction, but equal in magnitude to the weight force is going to be the static frictional force. Okay. Does this one make sense? What would happen, just to kind of just like think about this for a moment, what would happen if the static friction force was actually in the downward direction? What would happen when the floor fell out from underneath this person?
It would have gone down.
Yeah, they would have just slid down. It probably would not be as fun of a ride if that were to happen. So that's part A. So let's see, should be switching. So for part B, what we're looking for now is we have to determine the minimum number of revolutions per minute for which the girl does not slip. So this is very similar to the problem that we were just looking at, okay? Well, sorry, the do now that we were just looking at. So in this case, what does Newton's second law say about the forces acting in the vertical direction? What are these? What has to be true between these two forces in order for the girl not to slip or slide?
They have to equal each other.
Yeah, so in this case, the static friction force has to equal the weight force. Now we know a few things about the weight force. We know that the weight force equals mg, right? And then we also know something about the frictional force. Does anyone remember the formula for static friction?
Normal force times the coefficient of friction.
Yeah, very good. So it's going to be the normal force. Let me do that in a different color. But I'm going to just write the static frictional coefficient, or the coefficient of static friction for the first times. In this case, I'm going to call it R because I called it R up here. Okay, so in this case, R is the normal force. Can I give you guys one or maybe like 90 seconds to kind of try to, I don't want to just like kind of do it all for you. Can you maybe from this point, go ahead and try to find what's the minimum number of revolutions? So can I give you like maybe 2 minutes? And what I'll do is I'll set a timer. Okay. So we have about 1 minute and 55 seconds. I'm trying to give you guys speed drills right now. And if you need me to, I can put that other screen back up.
Yes, please.
Should be coming up. There we go. About 30 seconds left. About 7 more seconds. Does anyone want a little bit more time? Yeah, no.
Maybe one hint.
Like a hint, okay. Okay, so there we go. So what we're looking for in that answer, we're looking for, we want to know like revolutions per minute, okay? And so what that means is we want to know what the change in theta per change in time is, okay? This is our omega. So this is what we're looking for, okay? So what we need to do is find from this, okay? We need to find a minimum number of rotations per second, okay? So what we're looking for is we need, in this case, what we're looking for is we need the static frictional force to be greater than the weight, all right? Or at least equal to. Let me just check one thing quickly. So what I'm going to do is I'm going to write over here something parallel to this set of equations. So remember what Newton's second law says. So the centripetal force is equal to the mass times the centripetal acceleration. Okay. So in this case, so the centripetal force, the force acting towards the center of the circle, in this case is just going to be the normal force. It's going to be this R force. Okay, so this again is the normal force. This is the force acting or causing this person to move in a circular motion towards the center of the circle. And then this is going to equal m times the centripetal acceleration. And if you remember, I think you'll remember that this was equal to maybe R omega squared. Is it okay if I make that substitution? The thing I'm using is V equals R omega, and the centripetal acceleration is equal to V squared over R. Okay, let me do that better. So I just use these two relationships to get to this point, but it's in your data booklet, okay? So I'll give you maybe 1 or 2 more hints. So like what we need to do now is we need to know, well, what is R? Okay, so we have one equation for it, okay? And we can now find another equation for it over here. Okay, so we can divide both sides by mu s, And now I find that I have two equations for R. In this case, this one I have R equals mg, the mass times gravity. But they don't give me mass, but what you're going to see is that's pretty common because it's probably going to cancel out somewhere. If you remember all of the force problems that we did, like, especially the problem ones, mass usually canceled out. So if you check it out, now we have two equations for R, okay? And so the thing I'm looking for is this variable right here, okay? So can I give you another 2 minutes? And can you find a way with the information that this problem provides to find omega, our angular velocity? Is it okay if I give you 2 more minutes, or do you need like another hint? Does anyone need another hint?
2 minutes is good.
Okay. About 1 minute and 20 seconds. About 45 more seconds. About 20 more seconds. Three, two, one. Did anyone get a final expression for the answer?
Yeah, but I'm not sure what the units are.
All right, so tell me what you got, and I'll write it down. Just like the formula, if you will.
Yeah, so at the end, then I got, wait, for omega, like the answer, like a number, or just
Yeah, not the number. Yeah, the variables.
Okay, so I got omega equals the square root of g divided by the coefficient of friction times r, the radius.
Just like that?
Yeah.
Very good. That's what the answer is. Who wants to see how to get to that point? You give me like an emoticon or a finger on the screen. All right. So what I'm going to do is, so just to show everyone where this comes from, I'm going to set these two variables or these two expressions equal to each other. So I'll do this one over here. So I'm going to get mg over mu s. Okay, that's the substitution that I'm putting in here is this one over here. Okay, and this is going to equal m r omega squared. So what's going to happen is this m term cancels out with this m term. Okay, and then I'm going to divide both sides by r. What you do to one side, you have to do to the other side. So these ones right here cancel out. And so right now I have an expression, I'm going to just write this as omega squared equals g divided by r mu s. And then to find omega, I'm going to do the square root of both sides. So this equals my omega, my angular velocity. And Andy, did you get a value for this?
Yeah, 1.83.
So 1.83. And this one is radians per second. That's our base units for this, okay? Now, if we check out the answer, or what the answer, if we check out what they're looking for though, they're looking for not radians per minute, or sorry, oh no, so they're looking for revolutions per minute. So we have to do some conversions, okay? And so for this, before we get the correct answer, so what we need to do is multiply this by, well, we have to do some conversions. So in this case, I know that 2 pi radians is equal to 1 revolution. And just going to erase that equation above there, get it out of our way. And then the other thing I need to do, so like notice that the units of the radians cancel out, okay? Although they don't really need to cancel out. And then what I need to do is I need to convert this seconds over to minutes. So I know 60 seconds are in 1 minute. So those units of seconds cancel out. So our final answer, and the answer that's hopefully in the back of the book, is that omega equals, can someone tell me what 1.83 times 60 divided by 2 pi radians? Be very careful with your parentheses in this one. Make sure that you use parentheses to make sure that the order of operations in the calculator is correct.
So basically it's 17.4 or 17 revolutions per minute. 17. Yeah.
And that'd be revs per minute. Or another way to say this is RPM. Okay. Now, if I were to ask a slight variation to this, so this is the angular velocity. This is kind of like how fast this cylinder rotates. But in everyday life, if you were to say to me it rotates at 17.4 or 17 RPM, I wouldn't really understand what you're talking about. Can you tell me how to find what is this person's velocity? Like how fast are they going? Can someone answer that question for me? Or can you take a moment and find out, like, so the way I would ask this is, how fast is she going? So that might be like our everyday way of trying to understand this, because we don't think in revolutions per minute, like rotations per second. So like what variable are you looking for? What thing is being measured? Like when I ask how fast is she going, what am I asking for? If you want, you can chat me the answer. Like like when I say how fast, what are we looking for? Anyone ever see the movie Zoolander? Anyone ever see that movie with Ben? Oh, I forget his last name. Okay. Oh, never mind then. So when I'm asking how fast is she going, usually what we're asking for in this case is like, like the tangential velocity. So in this case, r omega. So the reason I bring this up is because you might be asked a problem like this. And so what you'll have to do is distinguish, you don't want to use this value. You want to use whatever this omega was when it was in units of radians per, well, in this case, you want to use the 1.83 radians per second. So like for this value, if I asked how fast, in this case, the R is 5 meters, and this omega is this 1.83. So just be able to distinguish those subtle differences in the way the question could be worded. Okay, because that'd be like a common mistake. Is there anything I can clarify with this problem? Does anyone have any other questions, follow-up questions for this? Anything I can clarify? No, yeah. All right, is there any other questions that I could go over from the homework? Any other requests? Yay, nay? No? Okay. All right, so I only have, so we have 15 minutes, I believe. Is that correct? According to our calendar, like clock? Is it 15 minutes?
Well, now is I time, so I think
Okay.
you go to the end of the day though.
So well, and so like instead of, well, first, does anyone have does anyone have a question on like number 11? Does anyone want help on this one? Did anyone get stuck? No, yeah. No one needed help on this one?
Yeah, I didn't know how to do it.
All right, so here, well, let me say two things. So like, so there won't really be a homework assignment tonight, but if you look at, on your page, like on Schoology, you'll see that there's an in thinking assignment. So it's the exact same in thinking assignment that I assigned like previously, but only 3 people did only 3 people did this. So if you've already done this assignment, if you are one of 3, you don't need to do this a second time. But if you didn't do this, that's totally fine. Just go ahead and make sure that you do it, okay? And so what I'll do is I can get this problem set up, okay? So like, let's set this problem up and then we'll call it a day. Okay, so here's our problem. All right, so this little car is going to have to drive in here, okay? And it's going to go up, and if it's moving fast enough, it will continue to stay on the track. If it's moving too slow, what's going to happen is it's going to come up and basically fall back down on itself. So the thing that we're looking for is what is the minimum speed so that when this car is coming in here, that the velocity at the top point is at least like 0 meters per second. We'll diagram this out to help it make more sense of it in a moment. But what it's looking for us to calculate is we want to calculate the minimum speed with which a cart must enter the loop-de-loop so that it doesn't fall. So what we need to do is find the minimum speed here. Okay, so that's going to be what our goal is for this, or for part A. So let's go ahead and diagram this out. So I'm going to just try to draw the loop. It looks something like that. And we have like a car over here. So we have a car over here. And what we're looking for is the velocity here. Okay. Now, if I could draw this better, there's like the center of the circle is here. And what's going to happen is this little cart's going to come in here. And what this needs is we need to have enough velocity so that this gets all the way to the top point right here. So like when we're setting up our condition, we want to know what is the velocity here. Let's call it the initial velocity, so that when the cart reaches here, its velocity, in this case, worst case scenario, we'll call this like say V final, is 0 meters per second. So this is the minimum velocity with which this, this velocity down here is the minimum velocity with which we can launch this, so that the velocity up here is at least 0 meters per second. And the other thing that they tell us, what else do they tell us in this problem? All right, so what I'd like you to do, okay, is I'd like you guys to draw 2 free body diagrams for 2 different points. Like we'll call this like point A, and we'll call like this point right there. Okay, let me use a capital, let me use an R, big R here. And I want you to tell me what the, I don't want to call that R. I want to call this point B, okay? Can you draw 2 free body diagrams, one for point A and one for point B? I think everyone knows that in both cases, the weight force is going to be pointing in the downward direction. All right, can someone help me out and tell me what other force is acting on the car or the cart at this point A? What other force, in what direction is it acting? You can even use your finger and point in a direction. What direction is, well, let me ask you a question. What's the name of the other force acting on the cart at this point, A?
Normal force.
Oh, the normal force, that's going to be push, or that's going to be in the upward direction. So when the cart is on the bottom, the normal force, we'll call it capital R, is going to be pointing in the upward direction. And then what's going to happen is we want the cart to have enough speed, so it's going to slow down, slow down, slow down, slow down, slow down until eventually it gets to 0. What would be the magnitude, or what would happen if the normal force right here goes to 0? Well, then there's nothing holding this cart. The cart's not making contact with the track. Okay, so in this case, the normal force equals 0 at point B. Sorry, I keep calling that R. And so at the top, the normal force equals 0, because at that moment, that's when the wheels lose contact with the ground. Okay. Okay, so I'm going to give you maybe like one more hint, and then I'm going to just leave this problem for you guys and try to work it out. Okay, so what we have here is we have like an object that's moving in a circular motion. And so it's subject to Newton's second law of motion for a circle. So like, we keep drawing the centripetal force is equal to, like M, there's a few things that we could say. We could say M times 8, the centripetal acceleration. This is the same thing, through a few substitutions. It'd also be this AC is also V squared over R. So these are two different ways to express this, okay? So this represents the centripetal force causing this car to move in a circular path, okay? If we look at point B, if we look at this point, what is the centripetal force? What is the force pushing this car's wheels in this case, or in this case, what is the force causing this car to move in a circular motion at this point up here? What force is it? It doesn't make sense, I think, when you first see it, right? The centripetal force at point B, there's only one force acting on the car. If like the car slows down enough that it loses contact with the track, then the only force causing it to move in a circular path, the only centripetal force is going to be the weight force at the top. So the centripetal force in this case is just the weight force. So the weight force equals this side of the equation, this mv squared over r. So I'm going to leave this problem. Here for you guys to try to figure out the next step, and then what we can do. So like finish this problem for homework, okay, and also do the in thinking if you didn't do that part, okay. And then we can go over this problem first thing at the beginning of class on Friday, okay? Any questions? All right, you guys are free to leave.
Bye.
Bye.
Bye.